Okay. Is everyone able to see the normal mode of the presentation?
Yeah, it looks good.
Yeah, thanks a lot. So yeah, so far we've done 2 exercises. So in the first exercise, we ran a bunch of independent MD simulations in parallel. In the second exercise, we ran umbrella sampling simulations. And at this point, you probably have noticed that for the simulations that we have run so far, those simulations could have been done in a serial manner because like those simulations were basically independent from of each other. So definitely we can choose to run them in a serial manner. I just ran them in parallel just to show you that that's a possible that is a possible option. Um, so that is for like the first 2 exercises. But now I'm going to talk about like advanced sampling methods that require the simulations to be performed in parallel, which means that you cannot run these simulations in a serial manner. And the reason that we need to run these simulations in parallel is because that there are some interactions between these simulations. And one of the most straightforward example is probably like multiple Walker's metadynamics. So as a quick reminder, metadynamics is the method that you learned yesterday, which applies Gaussian bias potential to the free energy surface, such that the system can easily sample the other metastable states once the free energy basin is filled up. If you want to further accelerate the process, especially in multidimensional cases where you use multiple CVs, then you should consider using multiple Walker's metadynamics. So here I'm showing you an animation of multiple Walker's metadynamics where 4 Walkers are used to sample the same free energy surface. And you can see that the exploration of the CV space is much faster. Well, it's at least like twice faster than the other one. So in the animation on the right, I have the Gaussian height, or it would have been like 4 times faster. So importantly, these Walkers are not like totally independent of each other, and specifically, each of them is aware of the history of the bias deposition across all different Walkers, so that they each of these Walker would know the current unbiased free energy, considering the contributions also from other Walkers as well. So other than this, like multiple Walkers metadynamics is nothing different from metadynamics framework that you learned yesterday, and this ends the theory section of the method. So that means that we are going to have the third exercise, which is a pretty short one. So I will jump to the Jupyter notebook. Okay. So it should be in the exercise 3 folder. Okay, so here comes the third exercise of the day, multiple Walkers metadynamics. So yeah, these are the things that I described in the presentation, like the Walkers in this algorithm are coupled instead of being independent. So these Walkers must be performed in parallel. And in this exercise, we are going to use the NaCO system again. We are going to run 4 Walkers for the metadynamics for this system. And from this metadynamic simulation, we should be able to estimate the free energy surface as a function of ion pair distance. And we will compare the result that we get in this exercise with the free energy surface we got from the umbrella sampling simulation. And that is also why we are running the simulation in the NVT ensemble, just to enable like a more direct comparison, so that both simulations will be performed in the same ensemble. So running multiple Walkers metadynamics. So well, here are just a bunch of comments that I used to get rid of the output directories as usual. So we will define the plummet binary. So this is the function that we used yesterday for the metadynamics tutorial. It's exactly the same one. Normally you wouldn't need to define such a function to run plummet, but like in this workshop, we are trying to like make sure everyone has the same version of the Plummet code, and so we are using the like a singularity image, and for to run them in a Jupyter notebook, we have to do that specifically in this workshop. But if you are like doing your own research project, you probably have your own build for your Plummet code from the source code. In that case, then you can just use the Plummet executable without writing any functions for doing that. Okay, so to run 4 walkers of metadynamics that communicate with each other using MPI, we will do the following steps. So just to clarify, there are 2 types of multiple walkers metadynamics you can run. The theory are exactly the same. It's just like how different walkers are, how different walkers communicate with each other. So I think the more common way is probably the MPI-based multiple walkers, where like different multiple walkers will communicate with each other via MPI. So each of them will be aware of the entire history of the bias. The other possible way is to do file-based multiple walkers metadynamics, which we will have an external file where each walker will constantly accessing to read and update the information about like the current biased free energy surface. So that again, using that method, each walker will be aware of the entire history of the bias. But here we are going to just use the MPI based version. And so we're running 4 walkers, so it's probably easiest to create 4 folders for as like walker 1, walker 0, walker 1 up to walker 3. You can make up your own name here, but here I'm using like walker as the prefix. So in each folder, we are going to copy over the input files and generate a TPL files. And then for each folder, we are going to create a Plummet input file. And then we are going to run md-run command outside the folder, because there is no like for loop needed when you're running simulations in parallel using MPI. So here are just a bunch of commands that I use to copy over the input files and generate the TPL files. It's nothing different from what we did in the previous 2 exercises. And since there's no error, so we are good to go. So here, after we generate a TPL file for each of the folder, we need to get a Plummet input file for each of the folder in this case. So here I'm using the Plummet input file that you used yesterday. They are basically the same, except that we have 2 additional lines at the bottom here of the METAD section. These 2 lines is the only difference. So first of all is the walker stir. This is like the directory where you want to save the hills files to. So in this simulation, you are going to just have 1 hills file output, because like all the walkers will using the same will output the hills data, the data of the Gaussian as a function of time to the same file. So we will only have 1 file, 1 hills file. And notably, when we are running like MPI based multiple walkers metadynamics, the working directory of each walker will be the each folder that we created. So here I'm just like saving the file like 1 level above the working directory. And to enable MPI-based multiple walkers metadynamics, we can just use the keyword walkers MPI. And not only we are not specifying like the number of walkers or something like that, but that will be done in our md-run command later. So we can just execute this command. And then, so now we have the TPL files ready. We have the Plummet input files ready. That means that we are ready to run the md-run simulations. So here I'm using like exactly the same, well, basically the same md-run command that you would use to run like a single metadynamic simulation. The only difference again is that I'm using multi-dir flag to enable simulations to run in parallel. And here we have like 4 folders specified here. So the Plummet implementation will be aware of like the number of walkers. So we will just execute the cell here. It shouldn't be taking too long, probably like 1 or 2 minutes. And meanwhile, I'll check the chat. Why is the correlation important? That is a great question. So when you are dealing with a time series, like you get from the simulations or something like that. Basically, if you don't decorrelate the time series, then and then you just use like correlated samples for your analysis, then you will probably underestimate the uncertainty, because like for correlated samples, the uncertainty will be lower. So that is why the correlation is really important. Okay, so the simulations are done. So we can start our data analysis for this part. And then yeah, so you can check that. So I'm not sure if the tree comment is available on your end, but if it is not, you can probably just take a look at mine. This is just a comment that shows you the directory structure, and it is not needed. It is not related to any steps later. But here I'm showing you the directory, and you can see that in each of the Walker folder, in addition to the typical simulation outputs that you will get from MD-Run, you will have an additional CoVar output from Plummet. So you can see that in Walker 0, we have CoVar 0. For Walker 1, we have CoVar 1, and so on. So we will get like 4 CoVar files in total. And there will only be one Hills file outside the Walker folders as we specified in the Plummet input file. So these are the output files. And as you know, the CoVar, not color, I'll fix the, yeah, the CoVar file basically document the collective variable as a function of time for each Walker. So we can visualize that here. So these are just plottings for the settings for the plotting. And definitely we can visualize the CV as a function of time for each of the walkers. So you can see that all the walkers were able to sample the entire CV range. So that is a good thing. We got like comprehensive sampling. So hopefully that will ensure that we get a good free energy surface in the next step. So how do we get the free energy surface? The method is basically the same. We use the Hills file, the only Hills file that we have, and we use a Plummet sum Hills function to get the fes.dat file. So there's no error, so we are good to go. So after this command, there should be a file saved in the folder that is called fes.dat that will have your FES free energy surface data. And now we are shifting the minimum of the free energy surface to 0. So it will allow like a easier comparison between different simulations. So here is just like a block of code plotting on the free energy surfaces. So you can see that basically the two curves are qualitatively consistent. We only ran the simulation for like 1 nanoseconds or so. So there's might still be some discrepancy between simulations. But if you consider like the error bars for the this one is umbrella sampling, then basically they are pretty much consistent. So if you like extend the simulations, they should be more and more consistent with each other. Yeah, remember that we've only run the simulation for like 1 minute, while you ran like 50 minutes for your metadynamic simulations yesterday. So to get a converge result, we might need to run the simulation longer. But here, as a for demonstration purpose, we are running a shorter one, and we are showing you that the two free energy profiles are basically consistent. So here is a reference, the paper that proposed multiple walkers metadynamics. And the main takeaways for this section is that using multiple walkers metadynamics, we are able to get a free energy surface consistent with one that we obtained from umbrella sampling and the metadynamics on Tuesday. Well, you can compare that. And then multiple walkers metadynamics would accelerate the exploration of the CD space, which is suitable for like multi-dimensional CD space. Okay, so with that, this is the end of the exercise, the third exercise, and I'll see if there's any question from the chat. How to estimate the uncertainty of FES in metadynamics? That is a great question. So some hills does not give you uncertainty, but so to get an uncertainty for free energy surface is actually like more it's actually requires some more coding stuff. So basically what you need to do is to perform like block bootstrapping. Basically what you need to do is that you need to divide the entire CV trajectory into several blocks. And then from each block, you are going to calculate like the histogram of the block. So you get the block histogram, and then you can like use bootstrap method to estimate the uncertainty from those block histograms. I have some codes for doing that, and I know there probably are some kind of tutorials in the Plummet on the Plummet website. I can reference that after the workshop. What makes the initial difference between the multiple walkers? Oh yeah. I think I forgot to mention that. But if you take a look at our code, like where we copy over the GROW files, they should be copying the GROW files from the configs folder. So configs folder contain like the NaCl GROW files, like different configurations of NaCl. So here we're actually using 4 different starting configurations for 4 different walkers, and that's actually recommended. It is recommended that you start each walkers from different positions in the CV space. So that will make the exploration, the convergence even like faster. Do you do this for each walker? I guess you are saying that on like block histogram, like block bootstrapping, right? Yeah. So we can do that for each walker, and then we can get like the standard deviation from each walker. So yeah, the answer is positive. We do that for each walker. Okay, so if there is no further question, I will jump back to the presentation slides. Let's see. Okay, is everyone able to see the presentation in a normal mode? Yeah,
Yes.
thank you.
Yeah, looks good.
Yeah, so so in addition to multiple walkers metadynamics, the most famous advanced sampling method that requires multiple coupled simulations running in parallel is probably the replica exchange method. So there are numerous variations of replica exchange molecular dynamics, and the first one proposed was the temperature replica exchange method. And the basic idea is to run multiple simulations in parallel and periodically exchange the coordinates of the replicas between ensembles running at different temperatures. So for example, now we can consider a simple case where we have 4 MD simulations running at different temperatures. And in temperature replica exchange, we alternated sampling in the configurational space and in the temperature space. So specifically, the sampling in the configurational space is done by MD simulation, and the sampling in the temperature space is done by multi-color simulation. So as you can see in the animation, for each of the replicas, we first run m steps of MD simulation to sample the configurational space. And after that, we propose exchanges between different replicas which is done in the temperature space. So at this point, like corresponding transition probabilities will be calculated based on the detailed balance conditions, so that you can see if the proposed exchanges should be accepted or not. And so, for example, here you can see that the exchange between the first and second replicas was successful. So after the exchange, the second replica now samples the first temperature T1, and the first replica should now sample T2. And on the other hand, the exchange proposed between replicas 3 and 4 was rejected. So the two replicas just keep sampling the same temperatures as before. So such exchanges of coordinates keep happening periodically until the simulation ends. So as you learned from the lecture on Monday, at higher temperature, it is easier to cross the free energy barrier. So you can imagine that in temperature replica exchange, given sufficient exchanges between replicas, all configurations should be able to sample the configurational space comprehensively. So this method is particularly useful for exploring configurational space or calculating thermodynamic properties as a function of temperature. So in addition to the temperature space, we can also have the simulation sampling the so-called alchemical space. The alchemical space is defined by a bunch of alchemical states, and an alchemical intermediate state is defined by a vector of coupling parameters. For example, here is a case where we have a two-component vector of coupling parameters. So the coupling parameters represent the extent we turn on or turn off different non-bounded interactions or the restraint. So for example, we can use the coupling parameters to control the non-bounded interactions between a molecule and the solvent environment. So when the coupling parameters are all 0, it means that all the non-bounded interactions between the molecule and the solvent environment remain on, and the system is still fully coupled. Then as we gradually increase the coupling parameters, we can create a series of alchemical intermediate states to gradually turn off the non-bounded interactions between the molecule and the solvent environment. And when all the coupling parameters are 1, the molecule will be fully decoupled from the solvent environment, and there will be no interactions between the two. So in this case, we can freely move the molecule inside the water box or out of the water box. It's basically sampling the molecule in the vacuum. So you can imagine that the free energy difference associated with this process changing from the first intermediate state to the last one, the associated free energy difference will be the solvation free energy of the molecule. So that is useful for so basically this shows that alchemical free energy methods are like alchemical intermediate states are suitable for calculating solvation free energy, and you can also use it to calculate like binding free energy or mutation free energy. These are like some pretty common things that people would do. So so you can imagine that instead of sampling the temperature space in replica exchange, we can also choose to sample the alchemical space in the replica exchange method. So in Hamiltonian replica exchange, we alternate the sampling between the coordinate space and the alchemical space. So here is an example where we have 4 alchemical intermediate states. So the last end state is not all a vector of all ones, but I'm just like listing the first few alchemical intermediate states. But normally the last lambda values for the last intermediate state should be a vector of 1. So just like temperature replica exchange, during the simulation, we just periodically exchange the coordinates between replicas, and the distribution of the neighboring replicas should overlap to have like reasonable probability of, so that we can have like successful exchanges between replicas. And as long as we have like sufficient swapping, each configuration should be able to sample the entire alchemical space. And we can stitch the probability distributions of from different replicas using M-bar again to calculate the free energy difference between the first state and the last state. And to get you familiarized with replica exchange method, here we have another exercise, and the goal of this exercise is to calculate the solvation free energy of this little four-site system that I'm showing you here. So let's get to the exercise. Well, I think right now it's probably like let me see. Okay, right now it's probably time for us to take a break. So let's say let's take a 10-minute break, and I'll answer questions in the chat. So let's try to come back at 3:04. Okay, and I'll stop sharing.